We are going to discuss the methods for the preparation of aldehydes. By this time, I am assuming that you have already practiced the nomenclature and structure part for aldehydes and ketones as per our first discussion. This is the second video of the same series, and we are going to look into the methods for the preparation of aldehydes now. So the first method for the preparation of aldehyde is oxidation of alcohols. There are many oxidizing agents, but as per our syllabus, what we are going to use is potassium dichromate, K2Cr2O7, in the presence of dilute sulfuric acid, H2SO4, and this is a very strong oxidizing agent. It can convert primary alcohol into aldehydes, and then aldehydes will get further oxidized into carboxylic acids. This is the action of potassium dichromate in the presence of dilute sulfuric acid. And the other reagent which we are going to use is pyridinium chlorochromate. It is also known as Corey's reagent. It is a mild oxidizing agent, and it can oxidize primary alcohol into aldehydes, and no further oxidation takes place into carboxylic acid. So the reaction stops at the aldehyde stage, and secondary alcohol will be converted into ketones by both of them. Okay, so we will look into a few examples. Before I go to the example part, just try to understand one part in this discussion which is important, that when we are oxidizing alcohols, so alcohols are basically having hydroxy group, OH, right? And this OH is present either on primary carbon or secondary carbon or tertiary carbon. So we are considering here only primary and secondary carbons. So when we are using these oxidizing agent, primarily what is happening is the loss of hydrogen is taking place, and loss of hydrogen is also called as oxidation. So accordingly we call this reaction as oxidation. And after the loss of hydrogens, what happens, that carbon which is connected to hydroxy will be then converted into C double bond O. So this is what is going to happen during the oxidation reaction. The same thing is happening in both the cases, either it is primary alcohol or secondary alcohol. Okay, so let us read this part which is on your slide. Oxidation by potassium dichromate. It is a strong oxidizing agent. It converts primary alcohol into aldehydes, and these aldehydes further get converted into carboxylic acid. If I am giving you one example, here what we can do is take a primary alcohol like ethanol, CH3CH2OH. On the arrow we will write K2Cr2O7 and dilute H2SO4. This is a super simplified version of this reaction, where what we do is we put just an oxygen atom in the square bracket, and we are assuming that this hydrogen is lost from OH group, and from the immediate neighboring carbon, that is CH2 carbon, this hydrogen is lost. What is remaining after losing the hydrogens will be CH3, then CH is losing one hydrogen, so one is remaining, so carbon number 1, carbon number 2. So this is the carbon number 1 and carbon number 2. So carbon number 1 is losing one hydrogen. So now only one H is remaining on this carbon, and this single bond O will become double bond O because this hydrogen is also lost from the system. And for the sake of balancing, we put H2O. This reaction is a very interesting reaction with very details of mechanism and all. However, in this discussion, we are just looking at the reactions, and maybe when the time permits, we will have one small video on the mechanism of oxidation of alcohols. As of now, what you are supposed to understand is lose the hydrogen from hydroxy group, that is OH group, and its immediate neighboring carbon. However, as I have told you that dichromate is a strong oxidizing agent, so further oxidation will take place. On arrow you put another oxygen, and what you will do is convert your aldehyde functionality into OH. Okay, so this is how the oxidation reaction is completed when we are using potassium dichromate as an oxidizing agent for primary alcohols. So a primary alcohol will give you an aldehyde, and aldehyde may undergo further oxidation to give you acid, COOH group. So this is how we are supposed to complete the reaction when primary alcohol will be oxidized with the help of potassium dichromate. So just remember the logic that loose oxygens generate a carbonyl, and then this H is further going into OH after further oxidation. I am rubbing it out, and we will see another example which has been put onto this slide. This is another primary alcohol. I will write the reaction with showing carbons as well: CH3, CH2, CH2, OH. Carbon which is containing or bearing the hydroxy is numbered as 1, 2, and 3. So I hope you can correlate the structures, right? And when we are using this particular dichromate reagent, then what will happen? We are losing hydroxy, 1H from hydroxy group and 1H from the neighboring carbon, right? So we will be having CH3, CH2, CH, and double bond O, right? So this is what is happening, and we are getting a 3-carbon aldehyde, that is propane-al. Pay attention to the nomenclature as well. So propane 1-ol is giving us propanal. As I told you, further oxidation may occur, and then this aldehyde, that is propanal, will get converted into acid, and you can see the difference here, that is H is now in the form of here OH. So this is carboxylic acid group, COOH, and the compound is an acid, propionic acid. Okay, so in this way we can complete the oxidation of primary alcohol with the help of potassium dichromate in acidic condition. Okay, now we will look into the another example where I am taking benzyl alcohol. Benzyl alcohol is aromatic ring with a CH2 branch and OH. So during oxidation, what we will do is lose hydrogens from OH group and the neighboring carbon, and we'll be able to make a carbonyl here. But as I told you, do remember that further oxidation may take place. So complete the equation with one more step and add one oxygen to convert this aldehyde into carboxylic acid group. So primary alcohol will give us aldehyde, and which may further undergo oxidation to give you acid finally. Now when we are taking the secondary alcohols, what will happen? So for that, what I am doing is taking a 3 carbon secondary alcohol, 3 carbon chain. The central carbon is the secondary carbon. So I am putting on this carbon, I am putting OH and H. The remaining carbons are getting 3 hydrogens each for the sake of completing 4 valencies. And when we are using this reagent, K2Cr2O7 and dilute sulfuric acid, then loss of hydrogen is to take place from OH group and the neighboring carbon, and the product which will be formed will be CH3C, now a double bond here after loss of hydrogen, and CH3. So this particular compound is a ketone, as you can see from the structure. It doesn't have hydrogen on carbonyl, right? So it is a ketone, and the name for this compound is dimethyl ketone or acetone. And if you want to give it an IUPAC name, then it will be propanone. So secondary alcohols are giving us ketones on oxidation, and primary alcohol are giving us acids on oxidation with the help of potassium dichromate. We will see one or two more examples, so let us try to solve one example now. Uh, when we are doing this reaction in the lab, potassium dichromate solution is having orange color, orange, yellow orange, and in that K2Cr2O7 formula, the oxidation state of chromium is +6, and when it is carrying out oxidation, it itself is undergoing reduction, and its oxidation state is changing from +6 to +4, and in the lab you will be able to see a distinct change in the color of dichromate solution. So this particular solution is containing chromium +6, and now after reduction of chromium or oxidation of alcohol, as we say, this chromium is having a state of +4. So let us solve example, and you try to solve it. Pause the video, read the question carefully, and make the structure and complete the equation. The question is, what is the action of acidic solution of potassium dichromate on butane 1-ol? So butane 1-ol, as you know that it is containing how many carbons? 4 carbons. A 4 carbon chain, 1, 2, 3, 4. Number it, and then as per the number you start putting the groups. So 1, 2, 3, 4. Then you put 1-ol, that is alcohol is present on the first carbon, so I am putting OH on the first carbon. Then I will balance the 4 valencies of each and every hydrogen by putting every carbon by putting hydrogen. So carbon number 1 gets 2 hydrogen, 2 gets 2 hydrogen, 2 hydrogen here, and 3 hydrogens. Okay, and when we are putting acidified potassium dichromate and K2 in the presence of sulfuric acid, then you know what you're supposed to do by this time. What you will do? You will remove a hydrogen from OH and another hydrogen from neighboring carbon, and then you will complete the equation. That is CH3, CH2, CH2, and now carbon number 1 is now left out with only one H because one has been removed by us, and oxygen is also without hydrogen, so that would be C double bond O. So what we are getting here is butanol and aldehyde, right? Because butane 1 all is a primary alcohol, as you know, right? This is a primary alcohol, so it is giving us an aldehyde which will further undergo another oxidation, and this aldehyde will be converted into carboxylic acid, CH3, CH2, CH2, C double bond O, and OH. So this is how we complete the oxidation of primary alcohols. Now we will solve another example. You try to again solve this question. Pause the video, read the question, and solve it, and then we will compare our answers. The question is, what is the action of acidic solution of potassium dichromate or butane 2-ol? I hope you are ready with the solution. You had paused the video and solved it. So let us compare our answers. What we'll do is take a chain of 4 carbons, 1, 2, 3, 4, number it because we want to make the structures as per the name. So we have the name with us, we will follow the name, butane 2-ol. On the second carbon, I am going to put one hydroxy or alcohol group, right? And then we will balance the remaining valencies, that is CH3, CH, CH2, and CH3. So we get this particular structure of butane 2-ol, and now we are carrying out the oxidation action of potassium dichromate K2Cr2O7 and dilute H2SO4. So what you are supposed to do is just lose the hydrogens. OH is losing one hydrogen and the neighboring carbon is losing another hydrogen. So we will have CH3, CH2, C double bond O, and CH3. So we are getting a ketone. No further oxidation is taking place when ketones are formed. So the secondary alcohol will end up giving us a ketone on oxidation. When you want to name this compound, number from the end which is near to the functionality. So 1, 2, 3, 4 from this side functional group is nearer, and the name for this compound will be butane 2-one because we have a 4 carbon chain butane and second carbon is containing the ketonic group. So butane 2-one. So this is how we complete the first oxidizing agent, that is potassium dichromate and dilute sulfuric acid mixture. Now we will go to another oxidizing agent, which is Corey's reagent, and it is chemically pyridinium chlorochromate. So it is a mixture of these two compounds, PCC. It is also written as PCC in the short form. So do remember the abbreviated form and do remember the name of the gentleman after whom we know this particular reagent, that is Corey's reagent, and do remember the full form of this abbreviation, pyridinium chlorochromate. In its description, the reference books are mentioning that it is a mild oxidizing agent. So primary alcohol will give us aldehyde. Further oxidation is not taking place in this reagent, and secondary alcohol are giving us ketones. This reagent is soluble in organic solvent like DCM. The reaction is usually taking place at room temperature. So aggressive conditions are not required. So it is a very mild and nice oxidizing agent. So let us look into the examples of oxidation by Corey's reagent, pyridinium chlorochromate. This is the equation in which we are using propane 1-ol. It is a primary alcohol. What we are going to do is, when we see PCC and this DCM stands for dichloromethane, the solvent. hydrogen will be taken out from OH and one hydrogen from the neighboring carbon, right? So what we will have is loss of hydrogen and then formation of a double bond here after the oxidation. So this is a very nice mild oxidizing agent working at room temperature and conveniently converting the primary alcohols into corresponding aldehydes, and we do not have any further oxidation. Now another example is here the same 3 carbon molecule but with an unsaturated moiety included into the structure. A double bond is there, and this example is included to show that it is a very mild oxidizing agent and not affecting the double bond at all, and it is just doing its job of removing the hydrogens from hydroxy group and the neighboring carbon and generating the double bond at that site. So a corresponding unsaturated aldehyde, acrylaldehyde is formed after the oxidation of prop 2-ene 1-ol. So these are the two examples of oxidation by PCC. We will solve one or two more. So here we have a question which is mentioning 3-methyl butane 2-ol. So we are supposed to carry out the oxidation of this alcohol. Okay, so we don't have to worry about the large name, just analyze into parts. We have butane, so now we have an idea how many carbons we have to draw. 4 carbons we have to draw, 1 2 3 4. Number it immediately and then start putting the groups as per the name. So we are following the name now. Butane 4 carbon, and on the second carbon I am supposed to put OH. So I am second carbon I am putting OH, and on the third carbon I am putting CH3. So this is CH3. This is how we get the structure. We just balance it by putting corresponding number of hydrogens as per requirement. 3 hydrogens here, 1 H here, another H here, and this last carbon gets 3 hydrogens. So this is 3-methyl butane 2-ol, and we are supposed to carry out the oxidation, that is pyridinium chlorochromate and DCM. As you can notice from the structure that OH is present on the second carbon. This second carbon is a secondary carbon, so our alcohol is a secondary alcohol, and the logic remains the same, that is you are losing H from OH and another H from the neighboring carbon, and what you are going to get is CH3, CH, CH3. We go further and we put a double bond here after losing hydrogens and a methyl at the end. So carbon number 2 has been now oxidized and we are getting a ketone here, and the name of this ketone will be, yes, number it 1 2 3 4, and on the third carbon you have methyl, so you will write that methyl branch first, 3-methyl. 4 carbon ketone is there, so butane, and that ketonic functionality is on the second carbon, so you will write butane 2-one. Please remember that if you are not able to write the name or facing the difficulty in writing the name, do refer to the first video again, practice some more, and then deal with these type of questions, and then hopefully you will be finding it easier than before. So this is how you get the oxidation of secondary alcohol into corresponding ketone with the help of pyridinium chlorochromate Corey's reagent. So far we have seen two oxidizing agents. The first one was acidified K2Cr2O7, and the second one is Corey's reagent right now on the slide, right? That is PCC. So these two methods are methods for the preparation of aldehydes and ketones from oxidation of primary and secondary alcohols respectively. So aldehydes will be formed from primary alcohol and ketones will be formed from secondary alcohol with the help of oxidation reaction, and this oxidation can be done with two reagents as per our syllabus, that is potassium dichromate K2Cr2O7 and the second one is pyridinium chlorochromate PCC. Now we are going to look into the third method for the preparation of aldehydes and then ketones, and that is by using Grignard reagent. You already know about Grignard reagent. The reagent is generally represented as RMgX, where R is an alkyl or aryl group. For example, CH3MgBr or any other member of this category like CH3CH2MgBr. So these Grignard reagents have one very special feature, that the alkyl group, the carbon part in these reagents is electron rich in nature, especially the carbon which is connected to the metal, that is magnesium. So magnesium is an electron donor. It is a metal, so it donates electron, and after donating electron it gets the partial positive charge, and carbon is becoming electron rich with a small amount of negative charge. Similarly, out of these two carbons, this carbon is CH2 is directly attached to magnesium, so this carbon will be getting the electrons directly from magnesium, so this carbon will have delta minus charge. So just remember that the carbon which is attached to magnesium will be electron rich, it will have partial minus charge, and magnesium will have partial plus charge. And when we want to go for the preparation of aldehydes from Grignard reagent, then we need to have a system where we need a hydrogen, because in aldehyde on one carbon I need hydrogen compulsorily, right? And I want to attach my Grignard to this carbon. So the other reagent which you are using is hydrogen cyanide HCN. HCN is a weak acid, but if you look at the covalent nature of this compound and the electron distribution in this molecule, then nitrogen being more electronegative is putting the electrons towards itself, and because of that nitrogen has partial minus charge and this carbon has partial plus charge. So what you see here on this slide is two types of carbons you see. In Grignards you see that Grignard reagents we are looking at the carbons which are electron rich, which have minus charge. I will just draw your attention here that this CH2 has partial minus and CH3 has partial minus, right? And the other reagent we are using, that in that reagent the carbon is having partial plus charge. So the most obvious thing which can happen is the minus charge will go and attack on plus charge. So this is what is happening, and this is the reason that we can have a bond formation between this carbon and this carbon. So minus carbon is attacking on the plus carbon. And as you know, the logic behind every bond formation is that when you make one, you break one. So what we can do is you can just attack by these carbons and then open the bond and generate an addition product, and which will be decomposed further, hydrolyzed with the help of HCl water to get the aldehyde. So I will complete the logic here. Starting with CH3MgBr, I am writing the complete reaction now. CH3MgBr we have taken. We are putting hydrogen cyanide in this reaction. Since it is the reaction of Grignard reagent, the condition will be dry ether, as it is always in the case of Grignard reagents. Some dry ether we are taking, that is free of moisture, free of water, and just remember the polarities. This carbon has delta plus, and this carbon which is connected to magnesium is having delta minus. And what we will have is the attack of this minus carbon on this plus carbon. When you make one, you break one. When we complete our equation, that CH3, this CH3 is attacking on this carbon, right, which is connected to nitrogen and hydrogen. So what we will do is we'll connect this CH3 to carbon, which is connecting to hydrogen and nitrogen. But this time nitrogen is having double bond in place of a triple bond, because what we did is when we made one, we broke one bond. So out of these three, only two bonds are remaining here. So that is how the number of bonds has changed in this case, and this nitrogen will be now connected to MgBr. This is an unstable addition product which is kept in the square bracket, and then you show further hydrolysis, that is water and HCl. At times H3O plus is also written on the arrow, and what will happen is this addition product is hydrolyzed by the action of water and HCl, and what you are ending up is with is CH3 and CH, and this part is removed, so you are getting a double bond over here. And for the sake of balancing, we show that nitrogen is giving rise to ammonia, and MgBr is forming MgBr OH. In this whole equation, there are few factors which should be taken care of, and you are supposed to pay attention to that. Is that this in the final product, you see here, this final product is ethanol, 2 carbon aldehyde, right? And it has only, how many carbons it has? It has 2 carbons, 1 and 2, right? And if you see the starting compound, then our Grignard has 1 carbon, right? And HCN has 1 carbon. So this 1 carbon of HCN and the other carbon of Grignard, they are adding up, and we are getting a 2 carbon molecule. That is one thing, right? Mathematically, the number of carbons has increased. 1 plus 1 is 2 in the product. Chemically, what you are supposed to remember is that this HC part, hydrogen cyanide, HCN, HC part is still intact here. This is the part which is coming from hydrogen cyanide after the loss of nitrogen, right? And oxygen we are getting from water hydrolysis, and this methyl we are getting from the Grignard reagent. We are getting from Grignard reagent, right? So if we change the Grignard reagent, this part will change, right? HCN will remain same. So we will be just changing the Grignard, and we will be able to make different aldehydes by changing different Grignard reagents. So one part is coming from Grignard, one part is coming from HCN, that is HC, and oxygen is coming from hydrolysis and water. So this is how you can just break this reaction into small pieces and understand it in parts, that how the logic works. And the whole reaction is possible because of the charge distribution, this very nicely uh, distributed charge density, where carbon is getting some electron rich nature, so it becomes partially negatively charged, and the other carbon remains partially positively charged. So that is why we are able to make the bond between them. The logic and the equation which I have discussed in the previous slide is now being asked differently. And you can just read this question and we will try to just analyze and break it into parts and then solve this problem. That how will you convert hydrogen cyanide to ethanol? So what we have here is two names. One name we have is hydrogen cyanide, the other name we have is ethanol. So what we are supposed to do is, ethanol is the product, right? We are supposed to convert this hydrogen cyanide into ethanol, so this is our final product. So what we will do is we will write the final product at the end of the slide. Then ethanol, how many carbons I need to draw? 2 carbons I need to draw. I need to convert this two carbon system into an aldehyde. So I am putting double bond O and H. So I have made an aldehyde now with two carbons, and I need to balance. The balance is always, so I will put three hydrogens here. So that is CH3CHO. This molecule we are supposed to prepare. So this is our ethanol, and what we are supposed to do is we are supposed to make it from hydrogen cyanide, HCN, HC triple bond N. As I told you that we are supposed to understand this system into bits and pieces. So I will highlight the part HC from HCN, and I will try to draw your attention to this part HC. So here what you see is that this part is coming from HCN in our final product. So in our final product, this HC we are getting from HCN. After hydrolysis, this nitrogen will be lost as ammonia, right? So do remember that. So basically what is remaining? When I am hydrolyzing, I will be getting oxygen, and that oxygen I will be getting from hydrolysis, water, right? So this oxygen is coming from water. What is the remaining part? The remaining part is methyl, and this I am getting from Grignard reagent. So what I am supposed to do is cut it into two parts and take out this fragment CH3, and I will take out this CH3 and convert it into corresponding magnesium bromide. So I have made a Grignard from this fragment. So this part is taken out and it is converted into Grignard. Now do remember that when we are cutting the bond to take out this group, at the same place we will put the magnesium. So I am cutting this bond CH3 single bond. So this is the CH3 single bond, and here I am putting the magnesium part on that CH3. So because you are cutting and breaking that bond, so at that place only, at that carbon only, you are supposed to put MgBr. Once you put MgBr, your Grignard is ready, and you know that magnesium is a donor. Magnesium will have delta plus, carbon will have delta minus. In our SCN, we will clear this and we'll put the charges. That carbon is electron deficient, delta plus. So the most natural thing which can happen is the minus part will go and attack on this carbon. When you make one, you break one. We will complete the equation now. So on the reaction conditions, as per the reaction condition, it will be dry ether, and we will complete the equation by following the arrows. The arrow is telling us that CH3 is going and attacking on this carbon, this particular carbon, and then we follow the bond formation process. This carbon already has one H, and triple bond is now becoming a double bond N MgBr. This is the product which we put into the square bracket to show that it is unstable and it will be further hydrolyzed. And then water and HCl will be added. You know that this molecule will be broken down into parts, and that CH3CH will be giving you CH3CHO plus ammonia is formed, and the other side product which is formed is MgBrOH. So this is how you can make different types of aldehydes by using SCN and Grignard reagent. So in case of aldehyde preparation, this SCN will be always repeated. Only we are going to change the structure of Grignard when we want to make different aldehydes. So SCN will be always there, and other thing which is changing is nothing but the Grignard reagent. We will see one or two more examples to clear the idea that how different Grignard reagents are used. and we can get different aldehydes. We have one question here on the same method of preparation for aldehyde by using Grignard reagent. So how will you convert hydrogen cyanide into 2-methyl propanol? So what we will do is first make the structure of hydrogen cyanide H C triple bond N, and you will make the structure for 2-methyl propanol. As per the name, we need a 3-carbon chain propane, and we will convert that 3-carbon chain into an aldehyde. Then we will number it 1, 2, 3, and after numbering we will put 2-methyl, that is a methyl group at the second position, and then we will balance the remaining part CH and CH3. By this time, hopefully you have understood the logic of the reaction, that this HCN part, we are getting HC from SCN. So this HC is now reflecting here. Oxygen we will be getting from water after hydrolysis. So what is remaining is a isopropyl group here. You can see that I have to cut this group, and from which point I am cutting it? I am cutting from this point, right? So after cutting it out, I will be writing it on this side CH3, CH and CH3. Do remember that I am cutting from this second carbon, right? So I will number it also for the sake of better understanding. 1, 2, 3. I cut the bond from second carbon, that is, this is the second carbon. So I have cut the bond from this side. So what I will do is I will put a bond there, and I will convert it into the corresponding Grignard reagent. Now you see that second number carbon is connected to magnesium, so this second number carbon will have extra electron density, that is delta minus, because magnesium is a donor. And on the other molecule, this carbon is electron deficient, delta plus charge is there because of nitrogen, which is a withdrawer. So most obvious thing which can happen in this situation is this minus carbon will go and attack on this carbon, and when you make one, you break one. So we will write the arrow with dry ether condition, and we will complete our equation. So this is the CH3, CH and CH3 part, which is attacking on carbon. So we will write carbon, which has one hydrogen, and now in place of triple bond we will have double bond MgBr. This we will put into the square bracket, and on hydrolysis H2O and HCl, we know that water will attack on this addition product and cleave it and break it into two parts from cyanides, from the bond between carbon and nitrogen, CN double bond, and what you will have is the formation of an aldehyde functionality plus ammonia and MgBrOH. So the most important aspect of this kind of question is you should be able to write the correct structure of the reactant and product. Once you write the structures, you just compare them, find out the similarities, note the differences, and then you can decide the strategy to complete the equation. There is no need to memorize anything. You just have to have very basic understanding of the charge distribution, where is the positive charge, where is the negative charge, and how this logic of a reaction takes place. Like when you make one bond, you are supposed to break one bond. So all these fundamental aspects are there, which can be easily handled by some practice. Hopefully, you will be putting more efforts, and we will try to solve few more examples of this kind. I am giving you one equation which you can try on your own. And the question is, how will you convert hydrogen cyanide into benzaldehyde? So the same logic works. You will write the structure of hydrogen cyanide. You will write the structure of benzaldehyde. Note the similarities, identify the differences, and then you can go further and solve this example. I can add uh, I can add one more question at this stage, and that is how will you convert hydrogen cyanide into propanol? So this is one more question. You can take it as practice and try to solve it and get the correct answer. Now we will go to the preparation of ketones from Grignard reagent, and we will have this system, that is, we are given CH3 MgBr and methyl cyanide, and you will try to understand the logic for the preparation of ketones with the help of this example. So we are given two molecules. I will write their structures here again to complete the equation. CH3 MgBr and CH3C triple bond N. Always show the bonds between carbon and nitrogen so that you can show the charge distribution, and you can show that nitrogen is a withdrawer and it is generating positive charge on carbon. On the other hand, this Grignard has electron donation by magnesium, and because of that, carbon is electron rich in nature in this molecule. So one carbon electron rich and the other carbon electron deficient. So what will happen is the minus charge will go and attack on plus charge, and when you make one, you break one. And on the arrow, we will have a similar condition, that is dry ether will complete the equation. CH3 has attacked on carbon, which is connected to another CH3, and now the triple bond will be changed to double bond nitrogen MgBr. So I hope you can correlate these structures, that I will just encircle methyl here. So this methyl which I am encircling is coming from methyl cyanide, and the other methyl I am putting in the square. So this is methyl which is basically coming from Grignard reagent. Okay, so now we see that there is no hydrogen which is present on this carbon. So this carbon has carbons on each side. Both the sides carbons are there. No hydrogen is present. So you can foresee is that we are not going to get aldehyde, we are going to get ketone on hydrolysis. So when I am putting water and HCl condition for hydrolysis, we are cleaving the C double bond N bond, and what you are ending up with is nothing but CH3 C double bond O, that is a ketone, plus the other side products like ammonia and MgBrOH. So this is how we are getting ketone as the final product. If you do some basic maths, you can add the number of carbons and see that Grignard has one carbon in Grignard, right? And in this CH3CN, we have two carbons. So you are adding them up. That is total, we are supposed to get a molecule with three carbons. So we have this three carbon molecule, propanone, where one is coming from the Grignard reagent and other two are coming from corresponding cyanide, that is methyl cyanide. We will try to apply the same logic as we have discussed right now, and we'll try to solve this equation where what we are given is a methyl cyanide molecule, that is CH3 C triple bond N, and we are supposed to prepare butane 2-one from this methyl cyanide. So I am writing the structure of butane 2-one. I need how many carbons? Butane, 4 carbons. 1, 2, 3, 4. And on the second carbon, so I will just number it first, CH3, 1, 2, 3, 4. And then on the second carbon, I am putting the ketone group, that is C double bond O, carbonyl group. I will balance the hydrogen, CH3, CH2, CH3. Now we will try to identify CH3 part, CH3C part in our product. So what you can see here, that is CH3 is connected to C. This part is coming from CH3CN, and I will cut the remaining part, separate it as Grignard reagent. So I am needing a Grignard reagent with a CH3CH2 group. So CH3CH2 plus, CH3CH2 bonded with MgBr, that is giving us our Grignard reagent. Now we know that when the Grignard reagent is there, you have a minus charge on that particular carbon which is connected to magnesium. So magnesium is donating electron and this CH2 is electron rich, and in the other molecule this carbon is electron deficient because of electron withdrawal by nitrogen. So nitrogen is delta minus and carbon is delta plus. And the most obvious thing which can happen here is when you minus will attack on plus, when you make one you break one. So we'll write the product, CH3 CH2 has attacked on the carbon of CH3CN. So this carbon is the carbon of CH3CN, which is connected to CH3 on one side, and CN is now double bond N, Mg, Br. So this is how we are getting the addition product, which will be finally hydrolyzed into the corresponding ketone. So this is how the reaction takes place. You will have the other side products like formation of ammonia and formation of MgBrOH. So the logic is very simple. The minus charge attacks on plus charge. You'll be able to successfully complete this equation only when you are able to draw the proper structures, note the similarities, identify the differences, and then you should be able to think about a proper Grignard reagent so that you can complete the equation. And I'm sure that with some practice you will be able to do it very successfully. So we can have one or two more questions which you can take up for practice. The first is, how will you convert methyl cyanide into acetophenone? That is one question which you can try to solve. How will you convert methyl cyanide into acetophenone? And another question is, how will you prepare 3-methyl butane 2-one, 3-methyl butane 2-one from methyl cyanide. So you try to solve them on your own. The steps are very simple. Convert the names into structures. See the similarities and differences. and find out which Grignard reagent will be needed to complete the reaction. So we can summarize the method of preparation we have seen so far. The first method was oxidation by K2Cr2O7 and dilute H2SO4, and the second method for oxidation was rhenium chlorochromate, and in this also we are oxidizing alcohols. So these two methods are having alcohols as the starting compound, right? Alcohols are required as a starting compound, primary alcohol and secondary alcohol, to get aldehydes and ketones. And then the second method we have seen is the Grignard reagent method, where we need a Grignard reagent and we need hydrogen cyanide to prepare aldehydes and other cyanides to prepare ketone. So when hydrogen cyanide is used, at the end of the reaction H will remain. So this H will remain on C double bond O H, and because of this H we are getting aldehydes. So we will be using HCN, hydrogen cyanide, if we want to make aldehyde from Grignard reagent. And if we don't want hydrogen, we want other carbon part, that is if you want to make ketone, then we are using alkyl cyanide plus Grignard reagent like RNGX. So we will be ending up with ketone, that is RCO and R. So this is how we are having now. So far we have covered three methods for the preparation of aldehydes and ketones, and we will see one or two more methods for preparation, which are in the named reactions. For like example, I have one example of Rosenman reaction. So we will see one more method. I am adding one more method. This method is for preparation of aldehyde, and that is Rosenman reaction. So reduction of acid chlorides to form aldehyde in the presence of palladium barium sulfate is called as Rosenman reaction. So basically you know that acid chlorides are nothing but the compounds with general formula RCOCl, and if we are carrying out hydrogenation of this RCOCl functionality in the presence of palladium and BaSO4, partial reduction is taking place, we can say, and what is happening is chlorine is replaced by hydrogen, so we get a hydrogen here. So what we are getting up as the end product is an aldehyde functionality. So this is a method of preparation of aldehyde, and it is a named reaction. It is known as Rosenman reaction. So we will have this example here where benzoyl chloride is used, aromatic ring COCl, hydrogen barium sulfate, palladium, and what you are getting is this replacement of Cl by hydrogen here. So this is the fourth method for the preparation of aldehyde, that is Rosenman reaction. This method is particularly only for preparation of aldehyde and not for ketones. So we can have different acid chlorides, and we can prepare corresponding aldehydes. For example, if I'm using acid chloride of acetic acid, so CH3C double bond O Cl plus H2 palladium barium sulfate, and what you will have is CH3C double bond O, replacement of chlorine by hydrogen. So you are getting acetaldehyde or ethanol, and this starting compound is known as acetyl chloride or ethanoyl chloride, and this reaction is known as Rosenman reaction. Talking about the named reactions, like Rosenman reaction is for the preparation of aldehydes. So we have a named reaction for the preparation of ketones as well, and this reaction is Fiedel-Crafts acylation. What we are supposed to do in this reaction is acylation of aromatic ring. We will have a simple aromatic ring of benzene. It is reacted with acid chloride in the presence of a Lewis acid like AlCl3, and usually the solvent is dichloromethane or 1,2-dichloroethane. This reaction is an electrophilic substitution reaction where aromatic ring attacks and replaces chlorine from the acid chloride, and what we get as the product is a ketone, which is acetophenone in this case. So this is one more method for the preparation of ketone, and it is a named reaction, Friedel-Crafts acylation.